Three-sided shapes are triangles. So four-sided shapes are quadrangles. Wait, I never wondered why until this day they're not called quadrangles. Well, in this video, we're going to be talking about quadrilaterals, not quadrangles. And we'll be seeing how it can be used to solve some complex geometry problems using both quadrilaterals and triangle techniques like we learned in the previous videos, similar triangles, special triangles, etc. Let's start off with the basics. So I'm sure most of you know the area perimeter formulas for squares and rectangles. Let's take a simple example. Let ABCD be a square. Let E and F be points on AB and AC. So E and F be points on AB and BC respectively. E and F. The line through E parallel to BC, so this line, and the line through F parallel to AB, so this line. Divide ABCD into two squares and two non-square rectangles. So not four squares, but two squares and two rectangles with different dimensions. The sum of areas of these two squares is 9/10 the area of square ABCD. Find AE over AB, or AE over EB, plus EB over AE. Okay, so as you can see here, we form two squares. So that means they must have all four dimensions must be the same. Let's say x. And the other square, well, notice how the square, well, let's say it has a side length of y. Let's say the big square has side length y. Then BX will be y minus x. So that means this square will have dimensions of y minus x, right? So then we're given that the sum of the areas of the two squares is 9/10 the area of the big square ABCD. So the two squares, well, they could be y minus x squared is the area of this square, and x squared is the area of this square, plus x squared. And this is 9/10 y squared. Okay, that is 9/10 y squared. We have to find AE over AB plus EB over AE. So a common mistake is to try and solve for y and x from this equation, which is obviously not possible. The key thing here is we don't need to know y and x. Just this. What is this? AE, which is y minus x, over EB, which is x, plus EB, x, over AE, y minus x. So we're asked to find the value of this. What is that? Well, that's just y minus x squared plus x squared over x times y minus x once we find a common denominator. Aha! We know what y minus x squared plus x squared is. It's 9/10 y squared. Right? But what about this thing? X times y minus x. Does it look familiar in our diagram? Well, this rectangle here has one side x and one side y minus x. The area of that rectangle is x times y minus x. Same thing for this rectangle, x times y minus x. Oh, but because we know that the squares sum to an area of 9/10 the total area, these rectangles, both of them combined, must sum to an area of 1/10 the big square ABCD. So we have that 2 times x times y minus x is 1/10 y squared. So x times y minus x is 1 over 20 y squared. So we divide this here. The y squares will cancel. We're left with 18 over 20 divided by 1 over 20, which is 18, the answer. Another thing that you could have done is, instead of letting this thing to be y, we could have just let it be 1 actually. Because the thing is, we're anyways only asking to find a ratio. So we don't actually care what the side lengths are, so we can let them be whatever we want. That's the common thing you can use for geometry problems. So if we let it be y, like I did here, then they would just cancel at the end. So there's really no need to do that. But I did it just for clarity. Okay, so that was a simple problem, but there's also many other different kinds of quadrilaterals. There's a rhombus, which is the area is just half the product of diagonals, and the perimeter is just 2 times the square of the square root of the sum of the squares of the diagonals. And this is derived from Pythagorean theorem, because this is d1 over 2, this is d2 over 2. So then it's just going to be, you just sum the Pythagorean theorem for all of these possible values, for all 4 sides, which are all congruent. And the main thing for rhombuses is that the opposite angles are equal, and all the sides are equal, and the diagonals are perpendicular bisectors. So they bisect and are perpendicular. Okay, and there's also a parallelogram. The parallelogram, this has area base times height, where height is the perpendicular, not necessarily the other side. That's important to know. Also, sometimes it might be useful that if you know the diagonals and the angle in between, it's just half the product of the diagonals times the sine of the angle, but we might explore trigonometry in a later video. So theta is the central angle over here. So some important parallelogram properties are that the diagonals bisect each other. So this is equal to this, and this is equal to this. Opposite angles are congruent, and opposite sides are congruent. So this is equal to this side, and this side is equal to this side, and opposite angles, so this angles and are equal, and these angles are equal as well. And these base angles are going to be supplementary. Okay, let's use it to solve this tricky AMC problem. In triangle ABC, BC equals 450, AC is 510, and BC or AB is 425. An interior point P is then drawn, and segments drawn are parallel to the sides. So this segment right here, ED, is parallel to CA. Similarly, we have FD is parallel to CB, and EF is parallel to BA, right? But the thing is, we're given that all of these segments, they're all D. All segments have a length D. That's interesting. So that's kind of the main condition in this problem that we have to somehow encode. All segments equals D. So, but D, we know the side lengths too, and we know the length of the segments, but how should we find the segment length if they're all equal? So the key thing to notice here is that each segment, we have to somehow maybe assign variables, right? Each segment can be broken down something like this. That's one way to break up CD, right? There's this inside part, and then there's these 2 outside parts, right? So let's just say this inside part is A, let's say, right? So if this inside part is A, what are these 2 outside parts? In terms of A, in terms of D, in terms of numbers, in terms of anything really, what are these 2 outside parts? Well, the key thing to notice here is parallel lines, right? EP parallel to CF, PF parallel to EC. Does that look like a special quadrilateral? That's a parallelogram. So that means that this side length is equal to this side length. Similarly, this is a parallelogram, so this side length is equal to this side length. So that means that the sum of these 2 side lengths is just this. Oh, but we know that is D. So that means that this whole thing is just A plus D. Similarly, let's say this is B. Then by parallelogram, CF is equal to E prime P, and F prime A is PD. So this is just B plus D. And similarly, this can be C, and this can be C plus D. Cool. So we know B plus D will be 5. We know B plus D is 510, right? Because B plus D is the whole segment AC, because AC equals B plus D equals 510. So then let's just say that B is 510 minus D. So we can get everything in terms of D, because that's anyways what we're trying to solve for. B is 510 minus D. Okay, that's cool. Similarly, we can get that A is 450 minus D, because the whole segment is 450 is equal to A plus D. So A is just 450 minus D. And similarly, C will be 425 minus D, because the sum of these 2 segments is D, and this whole thing is 425. Okay, that's good. Now we have all of our parts in terms of d. That's helpful, but we're still not done yet. How can we continue using the parallel line condition? So we need to somehow continue using this parallel line condition. So how should we keep pushing with this parallel line condition without having to worry too much about the segments not being used? The key thing here is that all of these triangles are similar. So essentially what that will mean is that the reason all these triangles are similar is because, look, this triangle right here, this base is parallel to this base. So that means that this triangle is similar to this triangle, right? But this triangle is similar to this triangle because these bases are parallel. So that means that this triangle is similar to the big triangle. And that's true for all three of these triangles, actually. So now we have to somehow use the similarity condition. And we can do this by just seeing that if we have, look here, PF over BC. PF over BC, that's this over this. PF over BC equal to F prime over CA by similar triangles. And that is 510 minus D over 510. And we know BC is 450, right? It's given in the problem. So therefore, PF is just 450 over 510 times 510 minus D. Oh, wow. And so let's do something else similar. Let's find PD. So PD, what is PD? Well, again, similar triangles. This triangle is similar to this triangle, just similar to this triangle. So that means that the small triangle here, similar to the big triangle here. And now we can just use similar triangles again. We have that PD over 450 equal to 425 minus D over 425. Therefore, PD equal to 450 over 425 times 425 minus D. Now you might be wondering, why did I arbitrarily choose to find PF and PD? Why did I randomly say, oh, let's find PF and PD? And the reason is because we can actually technically find all of these segments in terms of D if we want using similar triangles. But we don't have to. The thing is, if we find PF and PD prime using similar triangles, then we know that the total segment is D. So we have that PF plus PD prime, these two quantities over here, will be equal to the entire segment, which is just D. So if we add these up, it's just equal to D. So then we can just expand a little bit. 450 over 510 times 510 minus D. That's just 450. That's 450 minus 445 over 51D, which just simplifies to 15 over 17D, right? Plus 450 over 25 times 425, which is again 450, minus 450 over 425D. And 450 over 425 is just 18 over 17 when we divide by 25 in the numerator and denominator. And this is D. So that means 900 equal to 15 over 17D plus 18 over 17D plus D itself, which is just 17D over 17. And if we add this up, we get 50D over 17, and then equals 900. So D equals 17 over 50 times 900, which is 17 times 18, which is 17 squared, 289, plus 17, which is 306. So D equal to 306. Cool problem, but let's quickly review everything. So first, what we saw is that we can break this up into parts because we don't really know what they are, so we kind of want to let them be some variable. And when we broke it up into parts, we found that if we let this be A, this be B, this be C, then we found that we can solve for them in terms of D. And then after that, we use similar triangles because we can find this part using similar triangles and this part using similar triangles. So they add up to form just one of those D's. And then we've got a one variable equation we can easily solve to get an answer. Okay, let's move on to trapezoid. So you probably already know trapezoid area, average of bases times height. So let's solve a problem that uses trapezoids. Also, by the way, some other interesting properties of trapezoids is that if you draw both diagonals, the area of both of these triangles on the right and left sides will be equal. And also that we know that the ratio of the area of this triangle to this triangle is just b1 over b2 squared because of similar triangles, because we know these two triangles will be similar. And that's something that's sometimes useful. Okay, here's a cool problem. BC is parallel to AD in isosceles trapezoid, which means that these two segments are equal. Suppose point X and Y lie on the diagonal with X in between AY, as shown below. Let AXD equals 90 and BYC equals 90. AX3, XY1, YC2. Find area of ABC, D. We have everything marked in our diagram, so we don't need to do that, luckily. So there's what I like to do in most geometry problems. The first step often to solving them is angle chasing. In many types of geometry problems, most likely the angle chasing won't be enough to solve it, but the first step usually involves it, especially when you have a lot of parallel lines, isosceles triangles, circles especially. So these sides are parallel, right? So, I mean, that's going to give us already a lot of information. This is a transversal. We've got alternate interior angles, right? Alternate interior angles, that's parallel line property. Remember angle chasing video? And we also have the other pair of alternate interior angles. Because we know these are both x, so that means we have 90 minus x here, 90 minus x over here. And remember, these ones are not parallel because it's isosceles trapezoid. Okay, now what? We've got 90 minus x, x, 90 minus x, x. Aha! They're similar triangles. Two angles are the same. So if this is h, then this will be 3h over 2. That's cool. Okay, now here's kind of like the next major step that you might often have to do. So like kind of the second step would be to look for triangle properties, similar triangles especially, is a very common one. But sometimes it could be special triangles or other things like other properties like cyclic quadrilaterals or anything else. Okay, so look for similar triangles, which we just did. Now, generally when you're stuck on a geometry problem, you want to look for information you haven't used yet. The information you haven't used. And what information have we not used yet? I mean, we use 90 degree for the similar triangles. We haven't really used this sides yet, but we can't really use these sides yet. Other than finding similar triangles, we don't know how to use them. This one is just like a floating segment. The main thing that we haven't used though is isosceles trapezoid. Isosceles being the key word here. Means this equals this. Aha! Pythag theorem now we can use because we know CD equals AB. So CD equal to, CD by Pythag theorem is 3 CD squared equal to 3 squared plus 3h over 2 squared. AB squared equal to 4 squared plus h squared, right? By Pythag theorem. And we know these are equal because CD equals AB. CD equal to AB because it's an isosceles trapezoid. So then we just set these two quantities equal and solve. we have 9 plus 9h squared by 4 equal to 16 plus h squared, or 7 equal to 5h squared over 4, h squared equal to, therefore, 4/5 times 7, which is 28 over 5, right? But we're trying to find the area, right? Not just the side length. So how should we find the area? Well, the key thing here is that the area is just the sum of these two triangles, right? The area, let me move to the other corner maybe, so it's easier to see. So the area is just the sum of these, the top triangle and the bottom triangle, right? Top triangle and bottom triangle. The top triangle has area 1/2, well, the base is 6, and the height is h. The bottom triangle has area 1/2, the base is 6, the height is 3h over 2. So overall, it's just 3, 1/2 times 6 is 3, times h plus 3h over 2, which is 5h over 2. And we know that h squared is square root of, h is just square root of 28 over 5. So then 3 times 5h over 2, this quantity over here, which is our answer, well, we can just plug that in. 3 times 5 times root 28 over root 5 by 2. And 5 over root 5 is just root 5. So root 5 times 28 over 2. 28 is just 2 root 7. Cancel, cancel. This is left to 3 times square root 5 times square root 7, which is root 35. So 3 root 35 is the answer. Let's summarize really quickly what we did. First, we found the h, right? And then we saw that h to 3h by 2 because of similar triangles. And then after that, what we saw is that these sides are equal. That's the information we haven't used yet. And from there, we solved for h and then found the area of both of the separate pieces of the trapezoid. So not always will you be using half of the average of the bases times the height. Sometimes you might have to break it down into triangles, or even break it down into diagonals like I showed here, and find the area of each of these parts. Because you're not always, the problem is not always going to be nice enough and give you, oh, here's base 1, here's base 2, here's the height, found the area. It's going to be a little more tricky than that, especially on the AMC. But that's what makes it fun. So these are the main 3 steps that we kind of go through to solve harder geometry problems. Angle chase first, then look for similar triangles, special triangles, or other properties. And then after that, when you've kind of exhausted all your options, look at the information you haven't used yet and try to figure out a way to use it. Okay. And then that we're done. But we've got many more practice problems that you can solve. They're very interesting problems. You can get them for free in the book Mastering AMC 1012. And next we're going to talk about circles. So circles are one of the most common things in geometry because, well, they encompass all types of problems, from triangles to quadrilaterals to polygons, etc. Circles have many interesting things, including the radius being equal from all points. And they also have power of a point, which is a very useful property, which allows you to find length in terms of in a circle. Also, we know from a circle, we can use many other properties from triangles and quadrilaterals. And we'll also have something called cyclic quadrilaterals, which are quadrilaterals inscribed in a circle. Let's explore circles here.